My name is Steve Boggs. I'm the chair of the physics department, and on behalf of the faculty, the students, and staff of the physics department, I want to welcome everybody to the J. Robert Oppenheimer lecture series. I better get that name right. So many of you here today have attended our lectures in the past, and so you're aware of the rich history of this series and the symbolism that's tied to Oppenheimer around Berkeley. But for our new guests, I'd like to spend just a moment outlining the connection. It started in 1929 when 25-year-old J. Robert Oppenheimer joined the Berkeley physics department as an assistant professor. Just 1 year earlier, another promising physicist, Ernest Orlando Lawrence, had been recruited. Together, their collaboration, along with those of other prominent professors, would propel Berkeley physics to one of the best departments in the world and part of one of the best universities in the world, something that is still very true to this day. Oppenheimer was a theorist, or as he referred to himself, a propagator of the theory. That's an inside physics joke, by the way. Quantum physics was not well understood at the time, but there was potential, and Oppenheimer enjoyed explaining the theory to his colleagues and really anyone who would listen. He would convey what this was about, what had been learned, and what the unsolved problems were. Today, 87 years later from when Oppenheimer first came to our campus, we continue to ask those same questions. And this annual lecture affords us the opportunity to hear from some of the most brilliant theorists in the field. Speakers like Murray Gell-Mann, Kip Thorne, Stephen Hawking, Lisa Randall, Bruno Zumino, Edward Witten, and joining us today, Marvin Cohen. These are some of the, just a handful of the luminaries that have joined us for this lecture. In total, 6 Nobel laureates and many prominent theorists in the field of particle physics, condensed matter, astrophysics, cosmology, and AMO. As a side note, it's a bit ironic that Oppenheimer himself was actually considered a poor lecturer by our typical academic standards. It was something he tried to perfect throughout his tenure at Berkeley, which ended in 1943. The Oppenheimer Lecture is one of 2 public talks we offer annually through the Berkeley Physics Department, and it started with an endowed gift from Robert and Jane Wilson more than 20 years ago. Since then, we've been fortunate to have received additional support from many individuals, including 2 of our good friends who were planning to join us tonight, but they came down with a cold at the last minute. But nonetheless, please join me in thanking Steve and Arlene Krieger for their ongoing commitment to this important lecture series. So, you'll get to see the video. And now let me introduce our speaker. Today, Dr. Charlie Kane is joining us as our 19th Distinguished Oppenheimer Lecturer. Professor Kane is a Christopher H. Brown Distinguished Professor of Physics at the University of Pennsylvania. He received his bachelor's degree in physics from the University of Chicago in 1985 and a PhD in physics from MIT in 1989. After a postdoc at the IBM Watson Research Center, he joined the faculty of the University of Pennsylvania in 1991. Professor Kane is a theoretical condensed matter physicist who is known for his work characterizing quantum electronic states of matter, including quantum Hall states, Ledinger liquids, carbon nanotubes, and topological insulators. Recently, his research has focused on the theory of topological insulators and their generalizations. He's a fellow of the American Physical Society and a member of the National Academy of Sciences. His work on topological insulators has been recognized by several awards, including the Oliver Buckley Prize, the Dirac Medal, the Physics Frontiers Prize, and the Benjamin Franklin Medal. His lecture today is titled Symmetry, Topology, and Electronic Phases of Matter. Symmetry and topology are 2 of the conceptual pillars that underlie our understanding of matter. While both ideas are old, over the past several years, a new appreciation of their interplay has led to dramatic progress in our understanding of topological electronic phases. Please join me in welcoming Dr. Charlie Kane.
Thank you. Well, thank you so much for that very kind introduction, Steve. So Berkeley is a place where I feel like I've had many, many friends over a very long time. So it's really truly an honor for me to be able to visit here and to be a part of this very distinguished event. So thank you very much for inviting me, and I'm already having a good time. So what I'd like to tell you today is a story about symmetry and topology and their relation to physics, and in particular, their relation to the physics of electronic materials. And so symmetry and topology are sort of form some of the conceptual pillars for how we think about physics and how we think about matter. And so symmetry is probably the most familiar idea that we think about as a physicist. And so what symmetry is about what you can do to a system that keeps it to the same. And so if you look at these beautiful pictures these are some of my favorite pictures, you can see these patterns, and there are various things that you can do to these patterns that leave it the same. So for instance, you could move it over by a space, or you could rotate it by 90 degrees. And understanding the symmetries of a system allows you to sort of think very deeply about it. And so in physics, we're taught from our very beginning days of studying physics that symmetry is a very powerful tool for simplifying the study of things. And so when we teach freshman physics, we try to drive home the idea that the first thing you think about a problem is to think about the symmetries. And so there are many ways in which symmetry shows up in physics, and one of the deepest ways that symmetry shows up in physics is as a principle for classifying phases of matter according to their symmetries. So for instance, the crystalline phase of matter, where atoms group together in a very well-ordered crystal that kind of looks like these patterns here, a very powerful way is to characterize the symmetries of that crystal. Okay? And there are many, many more kinds of symmetries that as physicists we like to understand, and by characterizing those symmetries, that gives us a powerful way to organize our study of the phases of matter. So now symmetry is a very powerful tool, and what I'd like to introduce is what is an equally powerful tool, which is topology. And so this is maybe a little bit less familiar, at least in the elementary branches of physics. But what topology is about, rather than asking what operations leave a system the same, it's what can you do, what stays the same when a system is deformed. And so if you look at these pictures, you have the surface of an orange and the surface of a bowl. And what you can imagine doing is if you think of these as being made out of clay, you can imagine smoothly deforming this, squishing it down, smoothly deforming the surface of the bowl, the surface of the orange, so that it looks like the surface of a bowl. Okay? And so there's a sense in which these two surfaces are the same. Okay? Likewise, if you have the surface of a donut, it's kind of like the surface of a coffee cup. You can stretch and mold the donut until it turns into a coffee cup. The hole in the donut turns into the handle of the coffee cup. So there's a sense in which these two are the same as well. If they were made out of clay, you could imagine stretching and deforming one into the other. But you can't turn a donut into a sphere. You can't turn a sphere into a donut without poking a hole in it. And that's against the rules. Okay? And so topology is the study of what is the same about these and what's the same about these and what's the difference between them. Okay? And so topology, of course, is a very deep branch of mathematics. And what I'd like to try to introduce you to is some of the applications of topology to thinking about phases of matter that allow us to distinguish phases of matter. Now, topology in physics is also an old idea. This is something that has been around for a long time. So what is new is that over the last decade or so is that we've developed a new appreciation of how the interplay between these two ideas, between symmetry and topology, has led to a deeper understanding of phases of matter, and in particular electronic phases of matter. And so what this talk is going to be about is it's going to be about electronic phases of matter. And so what I'm going to do is I'm going to introduce you to the idea of what I'm going to call topological band theory. Okay, and I'll try to introduce that, and it's not as scary as it sounds. And this theory of topological band theory will allow us to have a deep understanding of interesting electronic phases. And so I'm going to introduce you to what we call a topological insulator and a topological superconductor. And so these are materials which can be studied in the lab. So and there's a huge amount of activity in the physics community, both theoretical and experimental, trying to understand the properties of these kinds of materials. Okay, and I'll try to explain to you what they are and what they're good for. And then at the end, I'll try to describe a little bit about the sort of frontier and where we're going in this field, and what kinds of things we may be able to expect. So my contributions in this field sort of started again about a decade ago, and it started off, I want to really highlight my colleague Jean Malie from the University of Pennsylvania. So this really started off as a collaboration between Jean and myself, and then over the years I was joined by a number of colleagues, graduate students, and postdocs, and I just want to highlight one in particular, Liang Fu, who really played a foundational role in a lot of the sort of beginning of this field. So okay, so we're talking about electronic phases of matter, and so what I want to begin with is the most basic electronic state of matter, and the most basic state of electronic state of matter is the insulating state. Now, you might say that the insulating state is the most boring state of matter. It's the state of matter where the electrons basically do nothing. Okay, but I'd like to try to convince you that maybe it's a little bit more interesting than that. So now, when we teach physics to our beginning physics students, we teach them about insulators. And so here's what we tell them. We tell them an insulator, an insulator does not conduct electricity because the electrons in the insulator are all bound to atoms. Okay, and so all the electrons are sort of stuck at home on their home atom, and they can't go anywhere, so the system can't conduct electricity. Now this fact is actually a unique consequence of quantum mechanics. Okay, and the reason for that is because what quantum mechanics tells you is that the motion of an electron in an atom is basically going around in a circle, sort of the way planets go around the sun in a solar system. And what quantum mechanics tells you is that when you have a particle that undergoes a periodic motion, it tells you that the energy levels that a particle can exist in come in discrete values, have discrete quantized energy levels. And so in chemistry, we call these orbitals. Okay, and so in a inert atom like say argon, if you have a crystal of inert atoms, then basically you have discrete energy levels, and you can have one energy level is all occupied with electrons, separated by a very big energy gap to the next one. Okay, and so what this discreteness of the energies means is that in order to dislodge a electron from one atom, you have to overcome this huge energy barrier. Okay, and that is the reason why insulators are electrically inert, because it costs this huge energy to dislodge an electron. Okay, now a crystal of inert atoms is probably is kind of boring. Okay, that's not the most interesting thing. When things get more interesting is if you bring the atoms closer together so that they start interacting with each other, and then they can form covalent bonds with each other. Okay, and so this is a little bit richer problem, and so it was really one of the sort of greatest triumphs of quantum mechanics in the last century was the development of the language for understanding the electronic properties of such materials. Okay, and so this theory usually goes under the name of the band theory of solids. Okay, and in band theory, what you basically recognize is that when you bring the atoms close together, these occupied states, they sort of broaden out into a band of energies. Okay, and we call that the valence band, the states that are occupied by electrons, and they still remain separated by an energy gap from the conduction band. Now, so the band theory of solids is probably one of the most consequential theories that we have in physics. Okay. It is the theory that underlies our understanding of all kinds of electronic materials. Okay, so for instance, semiconductors. Okay, the semiconductors that are in this laser pointer, the semiconductors that are in your cell phone in your pocket, all of the materials that underlie the information technology that we have grown accustomed to, ultimately arise from the understanding that comes from the band theory of solids. Now Berkeley, the University of California, Berkeley has, of course, had a long and storied role in the history of band theory, which continues until this day. So for physicists in my generation, and I think many generations, the first introduction to band theory came from Charles Cattell's book. Famous book. Okay, so it's quite an honor to be talking about band theory here. So now what band theory does is actually it takes advantage of symmetry. So remember, a crystal has lots of symmetry. It has translational and rotational symmetry, and by taking advantage of that symmetry, one can come up with a very detailed understanding of the structure of the electronic states in the valence band. Okay, and it's this detailed electronic structure that allows one to make such powerful devices out of it. But there's a point that I want to make here, which is if you think about this covalent insulator or a semiconductor, again, it's something which has an energy gap. There's something about it that is the same as this kind of trivial, crystal of inert atoms. Okay, it's the same in the following sense. That what you can imagine is sort of taking this crystal and very smoothly and gradually moving the atoms apart and gradually making the energy gap get bigger and bigger. Now you see, the thing is that the energy gap in argon is like 10 electron volts. In a typical semiconductor, it's maybe 1 electron volt, it's smaller. But you can imagine continuously dialing it up and making it get bigger. Okay? And so there's a sense in which these two are the same, kind of in the sense of topology that I described on the previous graph, where you can smoothly deform things and ask whether they stay the same or not. Okay? So there's a sense in which these are the same. Actually, they're kind of the same as the vacuum. Now, the vacuum isn't as empty as you might first have thought. So if you think in terms of relativistic quantum mechanics, Dirac's theory of quantum mechanics, then the vacuum has a valence band too. Okay? So the valence band for the particles in the vacuum define the antiparticle of an electron, which is the positron. Okay? And so if I remove an electron out of this valence band, then that is what the antiparticle of an electron is. Okay? And so really, there's a sense in which all of these are the same. The only difference here is that this energy gap is 1,000,000 times bigger. Okay, and so there's a sense in which all three of these are the same in the sense that one can smoothly deform between them. So this idea of smooth deformation introduces a very interesting question. Okay, and so I'd like to promote this idea that things can be smoothly deformed into one another into a principle, and this is the principle of adiabatic continuity. Okay? And so the idea here is I want to say that insulators are topologically equivalent in the sense if they can be continuously deformed into one another while keeping the energy gap finite. Okay? So what this, the question that this poses is whether there are topological phases that are insulators in the sense that they have an energy gap, but they're not adiabatically connected to the trivial insulator or to the vacuum. Okay? So in pictures, if I think of the trivial insulator as being like the surface of the orange, a sphere, is there an analog of the donut? Okay? And so the answer to this question, remarkably, is yes. Okay? There exist topological insulating states, and these topological insulating states are fascinating states of matter with fascinating properties, and that's what I want to introduce you to. So the sort of original topological state, okay, is a state that we've been studying for 30 years. It's called the quantum Hall state. And so let me tell you what the quantum Hall state is. It's actually not so complicated. So the quantum Hall state occurs when you confine electrons to a two-dimensional plane. Okay, and so that two-dimensional plane can exist on the interface between two materials. Okay, and if you put that two-dimensional interface in a strong magnetic field, then what electrons want to do in a magnetic field is they want to go around in circles. That's what electrons do in a magnetic field. Okay, and so this kind of motion has a name. It's called cyclotron motion. And this circular motion of an electron, it's kind of like the motion of electrons going around in an atom. That's circular motion too. Okay, and I explained to you that what quantum mechanics does to periodic circular orbits is it tells you that the energy levels are quantized. Okay, and so the quantized energy levels for this cyclotron motion are called Landau levels. Okay, and so what can happen is you can have a situation where you have some number of Landau levels are filled by electrons, separated by an energy gap from the rest of the Landau levels. Okay, so it's just so this is a situation where, like in an insulator, it is electrically inert because in order for the electrons to do anything, they have to overcome this big energy gap. Okay? So it should be like an insulator. Okay? But it's not exactly an insulator. Okay? And so here's the thing, that if you were to take this quantum Hall state and apply an electric field, so if you hook it up to a battery, okay, and apply which has a voltage, so that means that there's an electric field, then instead of going around in a circle, what the electrons will do is the circular orbits will start to drift, perpendicular to the electric field. Okay? And so that means that an electric current will flow, okay, perpendicular to the electric field, and this gives rise to an effect that's called the Hall effect. Now, so that one can think that there's an electric current proportional to the electric field, but it's perpendicular, and the ratio between these two defines what's called the Hall conductivity, and it's a truly remarkable fact that if you measure this Hall conductivity, so this is something that one can measure in the lab, that you find that its value occurs in quantized values, which are quantized in units of this combination of fundamental constants that has exactly the right units to be a conductivity. Okay? And this integer, which you measure by looking at the values on these plaquettes, this is an integer which can be measured to 1 part in a billion. Okay? So this is a truly, it's much more accurate than you would at first think it has any excuse to be. Okay? And so what's going on here is that this integer, one is really probing some sort of topological invariant. And so the question that this poses is, what is, this looks like it should be an insulator. What's the difference between this quantum Hall state and an ordinary insulator? Okay, and so this is this idea of topology. And so this is something which was, I think, first really understood by one of my heroes in physics named David Thales. And so what he realized back in the 1980s was that the difference between this quantum Hall state, which has an energy gap, just like an insulator, the difference between that and an ordinary trivial insulator is a topological property of its band structure. Okay? And so here's the thing, is that when you have an energy gap, I can think that this set of occupied states that the electrons are living in, which is separated by a gap from the unoccupied states, it's sort of one can think of it as a continuous function of momentum, and that function can be classified by what is called an integer topological invariant. Okay, and this integer topological invariant, in mathematics it has a name, it's called a Chern number. In physics we often refer to it as the TKNN invariant after Thales and his collaborators. And now I wrote down a formula here. Now, for those of you who understand formulas like this, that's good. And for those of you who don't understand formulas like this is fine. And I promise you that there will be no more formulas like this in my talk. And what I would like to say about it, though, for those of you who maybe this doesn't speak to, is I'd like to sort of quote an old physics teacher of mine from when I was an undergraduate, and he was trying to explain something that was a little bit beyond where we were at the time. And what he said is, it's not difficult; it's just more advanced. Okay. And it's like that. And so in the sense that this is something which, if you're at the right point, it's simple. And so let me tell you how simple it is, because what it really is like, it's like the following. So it's like a winding number. Okay? And so if you think about, imagine you have a rubber band wrapped around a pole. Okay, I could describe that, the number of times the rubber band is wrapped around. It could be wrapped around 0 times, it could be wrapped around 1 time, or it could be wrapped around any integer number of times. And now, of course, I can change the details of exactly where the rubber band is, and I can't change that winding number. Okay, so that winding number is a topological invariant. And what this Chern number is it's really just counting the number of times this valence band wraps around, as a function of momentum. Okay, and it really is something just like this. Okay, so now, so what Thales recognized is that this, and what he proved, is that this integer topological invariant is precisely the integer that is measured when you measure the Hall conductivity. Okay, so measuring this 1 part in a billion conductivity really is measuring this topological invariant. Okay, so now what I'd like to think about is we have this topological classification. There's something about the quantum Hall state that's different. So what? What consequence does that have? Okay, and the most important consequence is what happens on the boundary between different topological states. Okay, and this is something that was really first understood by another one of my heroes in physics, Bert Halperin. And so the idea here is that if you have a boundary, say between the quantum Hall state and the vacuum, so that means your sample has an edge. Then there exist conducting states on that edge. And this is actually something very simple to think about. If I think about this picture, in the magnetic field, the particles are going around in circles. Well, if I have a wall, a boundary, then then the motion, the electrons are going to bounce off the wall, and they're going to sort of skip along, and they undergo this kind of skipping motion. Okay? But the thing that's very interesting about this is that this skipping motion only goes in one direction. Okay? So the edge is like a one-way street for the electrons. Okay? And so this is a very special situation. Okay, and so classically we have this picture of the electron skipping along the edge. You can understand this kind of motion in the context of quantum mechanics as well. And in quantum mechanics, we give these edge states a fancy name. We call them one-dimensional chiral Dirac fermions. Okay? And if I think about the energy levels that the electrons can have in the vicinity of this edge, there are, of course, the valence band states, which are occupied in the interior of the sample, and the conduction, which are unoccupied. But then there is a single band of states that connects the valence band to the conduction band that are localized near this boundary. And these edge states have the special property that they are only propagating from left to right. Okay, so they're going one way. So the way you can think about this is if you have a wave, the velocity of that wave is given by the group velocity, which is sort of the slope of this energy as a function of momentum. Okay, and so these edge states are really magical, a very magical thing, because if you're an electron and you are in one of these edge states, then you have no choice but to go forward. Okay, that's the only thing you can do. So that means if you put in an electron over here, then you know with 100% certainty it will come out over here. Okay, because there's no other place that it can go. And so this means that in these edge states, electric currents can flow without any dissipation. Okay? And it's really this perfect transmission which is responsible for this 1 part in a billion quantization that is measured when you measure the conductance of these in this system. Okay? And this isn't something where you have to have a perfect edge. It can be dirty. It doesn't have to be perfect. Okay? So you can have an imperfect sample that has a perfect conductance. Okay? And so this is something that one would really like to be able to take advantage of. Okay, and so one of the problems with electronics is everything heats up, right? And so you'd like to be able to take advantage of maybe if you could arrange it so that your electrons could flow in these one-way streets so that they don't crash into the other electrons. Okay, but there's a little bit of a problem, which is that in order to arrange this, we had to start off with a system which is in a very strong magnetic field. Okay, so typically in order to get the quantum Hall effect, you need a very strong magnetic field. And so one of the questions we can ask is whether it's possible to have anything like this without a strong magnetic field, so that you don't have to have a huge magnet in order to make it happen. Okay? So that's something I'm going to get to, but let me just make one more point about this, which is that this idea that you have this sort of one-way edge state on the boundary of a between two different topological states. This I'd like to elevate to a principle. Okay, and this principle I like to think of as the bulk boundary correspondence, which is really the equivalence between some topological property of the bulk, which is this thing I call the Chern number, like a winding number that characterizes the bulk electronic structure, and a boundary invariant, which is the number of these chiral Dirac fermions. These things, you can't get rid of these either. Okay, you can imagine pulling them up and down as much as you want, but if it you can't get rid of them. Okay, and so the bulk boundary correspondence tells you that this bulk invariant, the Chern number, is equal to the number of chiral edge modes. Now, so this is something which can be understood on many, many levels. Okay, and so I kind of like the cartoon level. That's my level where I feel like I understand what I'm talking about. But it also is related to some very deep issues in mathematics, namely index theorems in mathematics, which can go very far beyond my pay grade. Okay, so this is something that we can understand on many levels. Okay, but I want to get back to this idea about you need a magnetic field in order to do this, and so I want to come back to thinking about the idea of symmetry. Okay, so one thing you know here is that if you were to take a motion picture of this kind of motion and then play the motion picture backwards, it would look different, right? If here the electric current is going from left to right, if you run the motion picture backwards, then it's going to be going from right to left. Okay? And so what this means is that this kind of motion violates the symmetry under the reversal of time. Okay? And so I want to say a couple words about time reversal symmetry. Okay? And so this is maybe a little bit less familiar of a symmetry. So let me introduce this idea. So again, time reversal symmetry is about what happens when you take a motion picture and run it backwards. And you can ask the question whether what you see in that motion picture running backwards obeys the laws of physics. Okay? Now, the microscopic laws of physics are the same when you run it backwards in time. Okay? But you can think about, a magnetic field actually is odd under time reversal, because magnetic fields are created by electric currents. Okay? If you have an electromagnet, what that is just a coil of wire that can carry a current and create a magnetic field. If you run that in reverse, the current goes the other direction, so the magnetic field goes the other direction. Okay? So a magnetic field is odd under time reversal. Likewise, this chiral edge state, if I run this chiral, this one-way motion of the electrons in reverse, it's going the other direction. Okay? And that makes sense, because in order to get this, I had to have the magnetic field, which broke time reversal symmetry. Now I want to talk about one more thing with time reversal symmetry, which is a unique property of quantum mechanics, which is if you think about an electron actually has a little bit more structure than you might first. It's not just a point particle. So an electron is actually like a little bar magnet, okay? Or you can think of it as like a little spinning top. So an electron has, in quantum mechanics, has what we call spin angular momentum, okay? It's like a top. Okay? And actually, electrons, there are basically two kinds of electrons. The electrons can either be spin up or they can be spin down. Now, if I think about how an electron, the spin of an electron looks if I run the motion picture backwards, then since the spin is an angular momentum, if I run it backwards, it's going to be going in the other direction. Okay? So the spin changes sign under time reversal. And it's actually an interesting question to see how that fact is implemented in the theory of quantum mechanics. So how does quantum mechanics affect the state? And basically, it does two things. Okay, it does something. It puts a star on your state. Okay, I don't want to tell you what that is if you don't know it already. But the thing what is really important is it gives you a little minus sign, okay? And so I teach quantum mechanics sometimes to first-year graduate students, and I always tell them that this minus sign is my favorite minus sign. So magical consequences happen because of this minus sign, and this minus sign has been responsible for important advances in my career. So this minus sign tells you that if I do time reversal twice, then I get a minus sign in this quantum, this minus sign, okay? And so this minus sign has a deceptive but very deep, deceptively simple but very deep consequence, okay? And so this consequence has a name. It's called Kramers' theorem. And what Kramers' theorem tells you is that if you have an electron, which is a particle that is either spin up or spin down, and you have time reversal symmetry, then every state has a partner which has exactly the same energy. Okay, and so we call that those two states that have the same energy, we say they're degenerate. Okay, and so every state is at least twofold degenerate, and so it's this Kramers' theorem that is really at the root of why you can have what's called a topological insulator. Okay, so now, so I told you that the integer quantum Hall state sort of requires that you have a broken time reversal. You have to have this magnetic field, so you can ask the question, are there topological phases with unbroken time reversal symmetry? Okay, and so this is something that you can have. And so, the first indication that that can happen was sort of a kind of a toy model that we introduced, which is to realize that if you take just two copies of this quantum Hall state, the thing that has these edge states that go one way, if you take two copies of it, one for the up spins and one for the down spins, then you can come up with a system that looks the same if you run it backwards. Okay? So this would have this system, which is two copies of the quantum Hall state, one for the up spins and one for the down spins. If I run it in reverse, then the right moving states become left moving states, but I also flip the up and down spins, so it looks the same. Okay, and so this is something, so if it has edge states, then it has edge states that look something like this. Okay, and so this is something that does not violate the symmetry under the reversal of time. So it's something that maybe you could hope to have happen in a system where you don't have to put it in a huge electromagnet. Okay. Now, so what you require in order to make this happen, though, is you require to have some interaction between this spin of the electron, what direction the bar magnet is pointing in, and the sort of motion of the electron, the orbital motion of the electron. So what it requires a system that has what we call a strong spin-orbit interaction. Okay, and so we first had this sort of toy model type idea, but shortly after that, Shucheng Zhang and a number of and his collaborators introduced a beautiful system that this can happen in, which is basically mercury cadmium telluride, which is a well-known semiconductor material that has a very strong spin-orbit interaction. What they basically showed is if you make a sandwich type structure with mercury cadmium telluride and mercury telluride, that this two-dimensional layer can exhibit this quantum spin Hall effect with these protected edge states. And so they made this prediction, and then within a year, then Lawrence Molenkamp and collaborators in Germany sort of built these structures, made these materials and built these structures, and did electrical measurements which established that, yes, indeed, the edge, the interior is an insulator. It cannot conduct electricity on the interior, but it can conduct electricity on the edge. Okay, and so that's what this quantum spin Hall state is. It's an insulator on the interior, but it is a conductor on the boundary. Okay, so this is the two-dimensional topological insulator. I think I'll skip this. You can have a three-dimensional topological insulator as well. So if you have a three-dimensional material, and so this is actually, so the three-dimensional topological insulator, there's an interesting sociological story here. So there was a bit of a race. So back, again, several years ago, we were thinking about this. I was arguing about this with my student Liang Fu, arguing about the finer details of whether you could have a three-dimensional topological insulator. And while Liang and I are arguing, I get this email from Joel Moore, many of you know, who basically showed that you can have a three-dimensional topological insulator, and that there are these 4 different topological invariants. And so my first reaction to this was, oh crap, I've been scooped. Fortunately for me, though, I was only partially scooped, okay? Because there's one thing that is a very important property that these three-dimensional topological insulators have, which is that they have a conducting surface. So again, it's an insulator. On the interior, it's electrically inert because it has this energy gap. But on the boundary, it has very special electrically conducting states. And these special electrically conducting states have a very special property which we call a Dirac cone. Okay? And so this is something which an ordinary material by itself will never do. Okay? But that can exist on the surface of this topological insulator. Okay, and so again, this is something which developed in a way which is a little bit unusual in physics. It's something where the idea for this state of matter actually came before the experiment. Okay, and it was really the idea that you could have this topological insulator that motivated people to then go and look at materials. And so one of the materials that was predicted, among several, is a material called bismuth selenide. And so again, this is a material that people have known about for a long time. Okay, it's actually a material that's used in thermoelectrics for cooling things. And it's an insulator, okay, but actually it's a topological insulator. Okay, and so the prediction then is that on the interior it's an insulator, but it has these surface states. And so what this picture is it's data from Zahid Hassan's group from Princeton, where they did what's called angle-resolved photoemission, which is basically a way of taking a picture of the energy as a function of momentum of the surface states. And what you see here is a textbook perfect Dirac cone. Okay, and so these surface states really exist. Okay. So since the discovery of these three-dimensional topological, 2 and 3-dimensional topological insulators, there's been a huge amount of activity of people making new materials, discovering new materials, studying their electronic properties, and so one of the things that you can think about is so these surface states have unique sort of properties of the way they conduct electricity, which are interesting in their own right. But you can also ask the question, well, what other kinds of things might you be able to do with them? Okay, and so one thing that you can do with them, which is really gives you something new, is you can so these I told you that these surface states they require the symmetry of time reversal. If you were to break the symmetry of time reversal by, again, now applying a magnetic field, which, again, looks different when you run it backwards, then you can open up an energy gap. And so what happens when you apply a magnetic field, you get Landau levels, but now the quantum Hall effect that you get is quantized with a different kind of quantization. So you have sort of what's called a half-integer quantum Hall effect. Okay, and so this is something which can only happen on the surface of something. It can't happen in a purely two-dimensional system by itself. Okay, and so by taking advantage of this, one can come up with ways of engineering these perfect one-way edge states for the electrons. Okay, and so one way of doing it is to sort of put magnetic materials on the surface of a topological insulator. Another way you can do it is to sort of incorporate magnetism into a topological insulator. And so this is a way in principle in which one can orchestrate these sort of perfect chiral motions, which, remember, these were things which gave you in the quantum Hall effect, gave you this 1 part in a billion quantization, this perfect conduction. Okay? So this maybe is a way of making that happen without that huge magnetic field. Okay? And so this is one direction that one can go at, sort of trying to leverage this new phase of matter, this topological insulator, in order to make these states that have this perfect conduction that maybe one can use for electronic applications. Another thing that one can do, which is maybe even more ambitious, okay, and I want to tell you a little bit about this, is what happens if you combine the surface of a topological insulator with yet another kind of material, which is called a superconductor. And this can give you something which is really new, okay? And so that's what I want to describe to you a little bit. So the point here is that combining a superconductor with a topological insulator allows a route to creating another fundamental topological state, which is called a topological superconductor. Okay? And so I want to explain to you what a topological superconductor is and why that would be a wonderful thing to have. Okay? So in order to do that, I'm not going to try to give you a lecture about superconductivity. Okay? But what I will tell you is that a superconductor actually is kind of like an insulator, okay? In the sense that it has a conduction band and a valence band which are separated by an energy gap, just like in an insulator. Okay, and so this is the structure of what's called the BCS model of superconductivity after Bardeen, Cooper, and Schrieffer, who really sort of revolutionized this field. And so the idea is that just like in an insulator, we have an energy gap. Okay, but the price that you have to pay for this kind of insulator picture of a superconductor, there's a price, and the price is that it has an intrinsic symmetry, okay, that the conduction band is exactly a mirror image of the valence band. Okay, so there's a sense in which the conduction band and the valence band are not independent of each other. They're exact mirror images of each other. And moreover, if I was to add an electron into the conduction band. So the conduction band is where the empty states, the states that I could add electrons to, are. If I add an electron to the conduction band, or if I remove an electron from the valence band is the one that has all this, is all occupied by electrons, so I can take one out. Okay? So in an insulator, those are two different states. But in a superconductor, if I use this picture, these states are actually the same state. Okay, so that is the price that you have to pay to have this sort of simple-minded insulator picture of a superconductor. Okay, and this gives you something that's very remarkable. Okay, so now you can ask the question: I have this energy gap. I can ask the question: well, are there topological states of this superconductor? Okay, I have an energy gap. Could there be states that I can't get to without having the energy gap go to zero? Okay? And one way you can think about that is you can think about, well, what could I have happen at the end of the superconductor? Okay? And so the thing that you know, so if I have the simplest version is a one-dimensional superconductor, so like a wire. And if it has a gap, then there aren't any states in the middle of the superconductor with energy in between this gap. Okay? But there could be states that are sort of, stuck at the end. But the thing we know is that if I have a state at positive energy, it has to have a partner at negative energy. Okay? Unless there's a state at exactly zero energy, and that state could be its own partner. Okay? Now, if you have this state at zero energy, there's no way you can get rid of it. Okay? Because I told you that, so you could ask, well, how could I get rid of it? Could I move it away? If I tried to move it away, then its partner would have to appear out of nowhere. And that's against the rules. Okay? So this zero mode of the electrons is topologically protected, And so it's this zero mode which occurs at the edge of a one-dimensional topological superconductor. Okay. Now, these zero modes are very special and magical things. Okay? Because remember, I told you that adding a particle at a positive energy is the same as removing a particle at the negative energy. So that means that if I add a particle into this state at zero energy, that's exactly the same as removing the particle from the same state. Okay? So if I add the particle and I add another one, then they disappear. Okay? So what this means is that this zero energy particle is its own antiparticle. So an antiparticle, if you have a particle and an antiparticle, you can put them together and poof, they're gone. Okay? Here you have a particle and you have the same particle. You put them together, poof, they're gone. Okay? And so there's a sense in which this is only half of a particle. Okay? And so this particle that is its own antiparticle is what we call a Majorana fermion. Okay, and I want to say a few words about Majorana. So Majorana was a very curious and mysterious figure in physics. So he was a genius. At least according to Enrico Fermi, who was one of the fathers of many of 20th century physics. And so now Majorana, again, was a genius, but he had a tragically short career. Okay? And so, but what he realized, so in 1937, shortly after, this was in the early days of quantum mechanics, shortly after Dirac learned how to unify the theory of relativity with the theory of quantum mechanics. So Dirac unified relativity and quantum mechanics, and shortly after that, Majorana published a modification of Dirac's equation which showed that it is possible for spin-a-half particles to be their own antiparticles. Okay, and so this, at the time, this was really just a, in principle, this is possible kind of thing. Okay, but it was a brilliant idea. Okay, but shortly after this, though, there was this mystery. So Majorana got on a boat in Italy, and he disappeared off the face of the earth, and nobody knows what happened to him. He was gone. Okay. Now, actually, somewhat more recently, there's a star here because this star has to be qualified by the statement, if you believe what you read on the internet. If you believe what you read on the internet, actually, more recently, the Italian police have concluded that actually Majorana was alive and well in Venezuela up into the 1950s. Okay, so maybe Majorana did survive. We don't really know. But in any case, Majorana's particle, a particle that can be its own antiparticle, is something that has intrigued physicists ever since. And I think it's fair to say that observation of Majorana fermion is one of the big challenges today. Okay? Now, in particle physics, fundamental physics, the fundamental particles could be Majorana fermions. So for instance, the neutrino might be a Majorana fermion, and this is something where experiments are going on in high energy in particle physics to try to determine whether or not a neutrino is a Majorana fermion. But what I want to focus on is something different, which is this condensed matter, topological superconductor version of the Majorana. And I want to explain to you why this is something we very, very badly want to make happen in the real world. Okay, and the reason that we want to do this is due to an idea of a modern day genius named Alexei Kitaev, and Kitaev had this profound insight, which is that if you have these zero energy Majorana bound states that I showed you can occur at the end of a one-dimensional topological superconductor, that they provide a method for storing and manipulating quantum information. Okay, and so they give a step towards making a kind of quantum computer. Okay, now the idea here is the following: that if you have two of these Majorana zero modes, they are in different places, and yet they define a single qubit, a single bit of quantum information. You know, a bit is the way computers store information, is a 0 or a 1. In a quantum system, you can have a 0 or a 1 or any combination or superposition of the two. Okay, and that's what a qubit is. And what Kitaev argued is that two of these Majorana bound states store a qubit of quantum information, but they store it in a way which is non-local. It's sort of shared between two different places. And what this does is it makes the qubit immune from decoherence. You see, the problem with trying to make a quantum computer, if you want, you have qubits, but the problem is, how do you keep it from accidentally measuring itself? So in quantum mechanics, if you do a measurement, you destroy the state of the system. Okay? And so if you can store it non-locally, so that if somebody looks over here, they can't measure the state of the qubit, then you can protect the qubit from decoherence. Okay? And so this is a big idea. Okay, and so this provides motivation for us to actually try to create these Majorana states in the lab. Okay, and so this is something where there's a huge amount of effort going on, and there are several different ideas. And so I'm not going to go through this in any detail, but there are several different architectures that people have thought about for how you might be able to realize these Majorana fermion bound states. So one idea, again, which is really the first idea that we had, was to combine a topological insulator with a superconductor. Okay, and so they're basically the idea with you see the problem is that, there are lots of superconductors, there are lots of materials that are superconductors, but we don't know of any topological superconductors. You can't just buy one. Okay, but our idea is to use an ordinary superconductor and combine it with some sort of topological material in order to engineer a topological superconductor. And so if you use a topological insulator, then the sort of flip way to say it is, you get the superconductivity from the superconductor and you get the topological from the topological insulator. Okay, but in any case, we have ideas for how, if one could use this to make these Majorana bound states, and other ideas are to use semiconductor nanowires on superconductors, or recently there have been ideas for how you can make chains of magnetic atoms on top of a superconductor. And so this is something where there have been lots of experiments, and the experiments seem to be seeing exactly what you would like. Okay, and the prediction is you should see, if you try to add an electron into this, you should see a little peak at zero energy, and that's what they indeed see. They see that here, and they see this in this tunneling into this atomic chain. You see a peak, and so this is exactly what you would want to see. Now, the challenge for these experiments, and why I don't think we're completely in a position to declare victory yet, is to rule out all the less interesting reasons why you might see this bump in the data. Okay. Another challenge. So now I kind of think that this is probably right. I think they probably are seeing this Majorana state. But another challenge for the experiments is to figure out how to actually take advantage of the quantum information that can be stored in these, okay? And so that's an even bigger challenge, okay? But this is something which we are highly motivated to do, and there's a lot of activity in that direction. Okay, so I want to sort of just finish up and tell you a little bit about the frontier of where other directions are heading. So there's a lot of frontier work going on in this topological superconductivity. Let me just say that there's sort of two different directions that I think you can go with this. So one frontier is that there are many, many more examples of topological band phenomena. Okay? By band phenomena, I mean phenomena that can be described within the band theory of solids. Okay? Because when it works, band theory works really well. And what it allows one to do is to have an interplay between sort of conceptual physics, computational physics, where you can learn how to actually accurately compute the band structures of real materials, and experiments. And so there's a huge interplay between those, and that's one of the ways in which the topological insulators came about, was through that interplay, because band theory works so well. And so there are many other phenomena that are topological that one can understand within the context of band theory, and one of them, let me just give an example of one of them, are what I'll call symmetry-protected topological semimetals. The most familiar example of this is actually graphene. Okay, graphene is a material which, again, has been studied a lot over the last decade. And the thing that's interesting about graphene from an electronic point of view is it has a conduction band and it has a valence band, but they exactly touch each other at a point, which is called a Dirac point. This structure is actually very similar to what happens at the surface of a topological insulator, okay? But it has this Dirac point, and there's a sense in which this Dirac point is protected by the combination of symmetry and topology, okay? And the point I want to make is that there are many more examples of things like this. So for instance, one could imagine so graphene is something which is a two-dimensional material. One can think about, what about a three-dimensional material? Could there be a three-dimensional material with Dirac points? And so we call this a three-dimensional Dirac semimetal. And so this is something where, again, one can conceive of this idea, and then one can go look to real materials in which this kind of thing happens, and that is something which there's a huge amount of activity. And there are many other kinds of, not just symmetry-protected semimetals, there are many other kinds of topological band phenomena, and that's one frontier that is going on. And so let me just conclude with what I think is the more ambitious frontier, which is thinking about electronic states that combine topology with strong interactions. Now, band theory, like I said, band theory works very well when it works. Okay? And band theory basically, on some level, ignores the interactions between electrons, but there are some situations where the electron interactions cannot be ignored. And so that opens the door to an even larger set of possible kinds of exotic electronic states that one could have. And so things can happen where you have strongly interacting systems that have what we call intrinsic topological order, and they can be even stranger than these topological insulators are. So for instance, you can have excitations where the excitations are particles, but the particles have a charge which is a fraction of an electron, like 1/3. Okay, you can have electronic states that have a very highly long-range quantum entanglement. You can have things that depend on the topology of the space. We know this can happen because this is something that can happen in the quantum Hall effect in a strong magnetic field. Okay, and what's called the Laughlin state of the fractional quantum Hall effect is a situation where we understand very well that this sort of exotic, strongly interacting states can occur. And so the challenge for us as a field is, can we engineer these topologically ordered states in materials or devices? Sort of like the way we were able to make topological insulators do this. So are there fractional, Chern insulators, fractional topological insulators, fractional Majorana fermions, and beyond? Okay, and so this is a situation, so as the way this field has worked, again, it's often the theory that comes first, followed by experiments. And right now we're at the stage where the theory is coming first. So there's been a huge amount of recent progress in theoretical models that describe these kinds of states. The challenge is to make those kinds of theoretical models get close enough to something that one can really, close enough to the real degrees of freedom of electrons. Okay, at this point, these kinds of models are a little bit too far removed, so much more work needs to be done in order to figure out how to achieve these states in the real world. Okay, but I think one should take this as a challenge and an opportunity. Especially for the younger people in the audience, maybe in the time of your career, maybe we'll be able to do something with this. Okay. So I think I'd like to, with that, finish up and just conclude with the idea that this symmetry and topology, they provide a very powerful framework for understanding some very novel electronic states of matter. I told you about the topological insulators, superconductors, semimetals. So there are many challenges for our field. Perfecting the known materials, discovering new ones, and in terms of theory, we want to be able to figure out how to protect and optimize these materials and understand exactly what's possible. So with that, I'd like to thank you very much.
Okay, we thank you, Dr. Kane. So we have time for a few questions. So I'll come around with the microphone. If people want to raise hands, we'll start with the students. Or here we go. We'll start down here.
How sensitive are these states? Are these states stable when there's asymmetries in the material?
You mean like the topological insulators, or
right. Because no material is perfect.
So. Absolutely, and so that's the beauty of topology. So the idea of these topological states is that you can change them. You can smoothly distort them, and they stay the same. Okay, that's the idea of topology. So for instance, no material is perfect. Materials can be, they have imperfections, impurities. And so we actually understand that in these topological insulators, in the quantum Hall effect, disorder does not make them any less perfect. Okay? So the example, the classic example is this 1 part in a billion quantization of the quantum Hall effect, which is very well founded experimentally. That occurs in systems that are dirty. Okay, they have lots of impurities. They're not perfect crystals. Okay, and the reason for that is because this state really is a topological state, which is insensitive to changing it. Okay, so absolutely, it is stable.
Okay, more questions? Yes.
Do you think that a full theory of strongly correlated electrons will need new mathematics, or can it be understood with existing theory?
Do I think it'll need new mathematics? New to who? I'm not sure that a lot of look, when I started off doing these topological insulators, I didn't know any topology. So that was new to me, okay? But of course, that mathematicians had understood that for a long, long time, okay? And so there's a lot of mathematics that mathematicians understand. And so I'm not sure that we need to invent new branches of mathematics. But what we need is a communication with mathematicians. There's a funny story. So when I started off with this topological insulators, I knew that there was something going on, And so I went upstairs to a colleague of mine in the math department, and I tried to explain to him what my problem was. I think I was able to pose it as a math problem. And what I wanted to know was whether or not there existed this Z2 topological invariant, which is either equal to 1 or 0. And so I posed him the mathematical problem, and what I wanted to know is I wanted to be able to calculate whether a given material is a topological insulator or not. And so I asked him, can we do this? And he did a little calculation, which is mathematics calculation, using mathematics that mathematicians understand. Okay, and he came back with the answer, and his answer was yes. Yes, there is a Z2 topological invariant. And I said, yeah, I was pretty sure I knew that, but what I want to know is how do I calculate it? I want to know which one is it. Is it 1 or is it 0? And he looks at me. He's like, why would you want to do that? So I think that so mathematicians, so they do understand things, but they don't necessarily know how to, we need to bridge the gap a little bit. So I think I'm not sure there's going to be new mathematics, but maybe it may be new to the physicists.
One of the exciting experimental demonstrations from last year were Weil fermions.
Yes.
Maybe lossless current conduction and so on. Is there a relationship between that and the topological properties you're talking about?
Absolutely, yes. So a Weil point, what a Weil point is it's sort of like one of these. Okay, it's a point where the conduction band and the valence band touch each other, and that Weil point is protected topologically. Okay, so in fact, there is a topological invariant associated with the Weil point, which is actually the same topological invariant, the Chern number, which defines the quantum Hall effect. So yes, absolutely, the Weil points, the phenomena of a Weil semimetal is a topological phenomena and belongs, on this list of topological phenomena. Absolutely.
Okay, so this side of the room is clearly winning on the questions front. So is there anything from this side of the room? Boo. Okay, here we go. Thanks for saving the day, Doug.
So are all these states restricted to very low temperatures at this point, or does this
Right.
topological invariance survive at higher temperatures?
Yeah. Well, okay. So the criterion for whether you need low temperature or high temperature is how big the energy gap is. Okay. And in bismuth selenide, the energy gap is it's a fraction of an electron volt, which actually, if you convert that into a temperature, is actually pretty big. Okay, so if you really were able to have a very good crystal of bismuth selenide, then in principle you should be able to do it at room temperature. Now, that said, the real materials that we have aren't quite that good. Okay, but so in principle, I think it is possible. So one of the challenges that we have in the field is trying to come up with topological insulators that have big energy gaps. Now, for topological superconductors, you need to have something that superconducts. Okay, and so there we don't have any room temperature superconductors at this point. Okay, and so that is going to remain a low temperature phenomenon.
Unfortunately, I think that is about the end of our time. So let's thank Dr. Charlie Kane one more time.